Maths of the Coronavirus, Part 4, the areas of unusual shapes and Riemann sums. If you've studied maths for any length of time, you've almost certainly learned how to find the area of shapes, and many of the formulae here are probably very familiar to you, having been drummed into you over many years of study. But if you've been thinking at the same time, you've probably realized that they only work for perfect geometric shapes. Unfortunately, the real world is not made up of perfect geometric shapes. Here's a Formula 1 car, and apart from the wheels, I don't think there's a perfect geometric shape anywhere in that picture. So what do we do when the shape we're given is weird and wonderful, but we still have to find the area of it? And what on earth does this have to do with the coronavirus? Let's start with our old friend, the new confirmed cases daily count graph. As you can see, each column in this column graph represents how many people got infected with the coronavirus on a particular day. And as you can see from the fact that the columns are getting mostly smaller towards the right of the graph, Australia is doing very well in terms of limiting the spread of this virus. Here's a version of the graph we saw a moment ago, just with less data in it, so it's a simpler graph. So here in the table we have 1 week, and then we have the number of new infections on each day of that week. So 3 people got sick on Sunday, 5 more on Monday, 10 more on Tuesday, and so forth. Over here we have the column graph of that data. But they're not just columns, are they? Each column is a rectangle. So let's start with our Sunday column. Now, because it's only one day, Sunday, it's 1 day wide that way. And we know that 3 people got infected on that day, so it's 3 high. So if I wanted to find the area of that, it's 3. Now Monday is also just 1 day, so 1 wide. But on that day, 5 people got infected. So that gives me an area of 5. On Tuesday, it's 10 people, and that's an area of 10. Well, that's easy enough. Finding the area of rectangles isn't a problem. Why bother? Well, what happens if I add those areas up? I take my 10, my 5, and my 3, and I add them to get 18. Look over here at the data. Let's have a look at the total number of people that are infected on each day. On Sunday was only 3. By Monday, 5 more people had joined the 3, and we have a total of 8 infected people. Tuesday, 10 more join, and now I've got 18 infected people. So by adding up the area of each of those rectangles, I'm finding out the total number of people that are infected by a certain day. Let's complete the process. On Wednesday, it's 11 more people, so the area is 11. Thursday, it's 9. Friday, 5. And Saturday, 4. So we started with 18. We added 11 more, that gave me 29. 9 more gives me 38. 5 more, 43, and 4 more, 47. So there should be a total of 47 people infected for the whole week. Let's check it against our numbers over here. 18 plus 11 is 29. Plus 9 more is 38. Plus 5 more is 43. And 4 more is 47. So it works. The area of the rectangles all added up tells me the total number of people infected for the week. Now, you might well ask yourself, why bother with all that work? Why get data, create a graph, do the rectangles, find the area, add them up, when really you could have just added those numbers up there to get the same result? That's an excellent question. Why bother? Well, we bother because that little process gives us a way to deal with unusual shapes. So let's start with the rectangles, and we know what the area of the rectangles is and how to find it. Let's put in over the top of those rectangles the irregular shape we were looking at earlier on. Now, just glancing at that, it seems that the area of the irregular shape is fairly similar to the area of all those rectangles added up. Not perfect, and we could do better, but it gives us a start. So let's go back a bit and have a look at how we got to there. Here's a lesson I recorded for one of my classes. So how do we find the area of an irregular shape? Something that's not a circle or a rectangle or a triangle that we have an easy formula for. Well, here's an example of an irregular shape. To keep it easy, I've started with 3 straight sides and just 1 irregular side. The first step is to put it into the top right-hand side of a number plane or Cartesian plane, just so we can put some numbers around it. So here you can see 0 through 6 on the y-axis and 0 through 8 on the x-axis. Now what I'm going to do is I'm going to draw a rectangle that is just big enough to cover that whole shape. And you can see that my rectangle is 5 up this side and 8 along that side. So the area of my rectangle is 40, whatever my units might happen to be. So the area of my shape, the green bit, has to be less than 40. And 40 is my very first approximation of this, but it's not a great approximation because it's over by a fair bit, because none of that should be included, and none of that should be included. So how do we take that and make it a better approximation? The next thing to do is to divide your shape in half. So go along your x-axis and divide it in half, like that. Now, it's important in the technique we're learning that it is exactly half. That this distance there to there is the same as this distance there to there. So 4 and 4. So having done that, what we then do is find the middle of this bottom half, in this case 2. And then from there, go up until you find your shape and find the y value there. Now I've pre-done it, so it's 4.21. But you can find that easily if you're doing one of these yourself. Do the same with the top half. Find the middle, in this case 6. Go up and find where it touches your shape and find your y value. Now draw a line, hopefully straighter than the one I'm about to draw, across so that it goes through those points. Now you've got 2 rectangles, one here and one there. And we can find the area of each rectangle. That's 4 across and 4.21 up. So 4 times 4.21 is 16.84. So that gives me 16.84 in that rectangle. And this one here is 4 across by 3.022 up, the y value. And that gives me 12.088. And then I add those 2 rectangles together, and that will give me my best approximation, or my next approximation, I'm sorry, of the area of the green bit. So my new approximation is 28.928. But it's still not a perfect approximation. Let's have a look why. Let's go to a slightly tidier version of that over here. Might even zoom that in a bit so we can see it. Let's have a look. We calculated the area first of this rectangle here on the left. But there's a couple of problems with that. The first is we've included this area in here, which should not have been included. And we've also left out that bit. So we've left some bits out that we should have included, and we've included some bits that shouldn't have been. Now, looking at that, roughly they could balance one another out, but not 100% accurate. Looking at the right-hand rectangle, this one in here, again, there's going to be some error associated with that, because we've excluded that bit. It's not included in any of the rectangles, but it is part of the green shape. But there's no balancing bit that we've included and shouldn't have. So that estimate's probably not right. So let's make the estimate better again. Rather than having 2 rectangles, let's go to 4 rectangles. And here's one I prepared earlier. Now remember your rules. Each rectangle has to have the same width. In this case, I'm making my rectangles have a width of 2. So there's 4 of those to make up my 8. And again, I find the middle of each rectangle. So in this case, my x equals 1, 3, 5, and 7. And then starting from there, I go up until I find the y value, which is 3.27. So now I've got a rectangle that's 2 wide and 3.27 high. So that's going to be 6.54, I think. Double check that. Indeed, it is 6.54. This one here is 2 across and 4.995 up. And that's 9.99. This rectangle here is the same as the first one. So that's 6.54. And the last one is 2 across and 3.001 up. So 6.002. Now, if I add all those up, and let me introduce you to this notation, the sum, that's the Greek letter sigma, and we're going to use that to mean sum, which means add them all up. The sum is going to be 6.54 plus 9.99 plus 6.54 again plus 6.002, and that's 29.072. So let's have a look at our errors in that one. Again, it's not perfect. So my first rectangle, there's a bit that should not have been included, and a fair bit there that should have been. There's 2 bits that shouldn't have been included. There's a bit that should have been. There's a bit that shouldn't have been. And at this level of zoom, that one looks all right. So there's still error in this. This isn't perfect, but it's probably better than our previous estimates. Now, we could keep going doing this, smaller and smaller rectangles, and our error would get smaller and smaller. Now, there are other tricks and other methods in maths to stop us having to do these calculations endlessly. But let's pause there for a moment and have a look at 2 mathematical ideas that come out of what we've just seen. And the 2 mathematical ideas we want to explore as a result of this are the Riemann or Riemann sum and the idea of a limit. Now, the Riemann or Riemann sum is what we've just done. That is, taking an irregular shape, breaking it up into rectangles, and then adding those up to get an approximation for the area of the shape. So Riemann was an 18th century German mathematician, and sum, as you know, just means adding up. The next concept is that of a limit. So let's have a look at the results we've gotten so far. Let's very roughly draw ourselves a graph here. Now, somewhere or another, there's a real value for the actual area of my shape. So let's call it that. Let's say that was my real value for the area of the shape. And let's have a look at what our estimates were for the area of that shape. Our first estimate, which is about there, comes in at 40. And we know that was a rubbish estimate. Our second estimate was 28 and a bit. So let's just say that was a bit too low. And we're guessing at that because the third estimate was 29 and a bit, which was there, and maybe that's a bit too high. Let's pause for a sec and think of something you do know, because I'm sure everybody's actually done this at one point or another. At one point or another, everybody, because they're bored in class, has taken the school desk, put a ruler on it, and flicked the ruler to make that noise. And when you first flick the ruler oscillates between about there and there. It goes up and down. But as it runs out of energy, the ruler gradually slows down. This distance from there to there decreases. And then finally, once it's run out of energy completely, the ruler's just a straight line off the edge of the desk. Let's have a look to how this applies in this situation. So my first estimate was 40, which is way too high. My next estimate was 28, which we think is a bit low. Then we had an estimate of 29. If we broke it up into 8 rectangles, my guess is we would go a little bit under again, and then 16 rectangles and so forth. And you can see what's happening. It's just like the ruler. It starts out doing a big loud but then as it runs out of energy, it gets closer and closer to the straight ruler. In this case, as we get more and more rectangles, or to think about it in another way, as the width of these rectangles gets smaller, so remember our first rectangle was 8, then this one's 4, then our new guess is 2, then the next guess would be 1. As that width gets smaller and smaller, we get closer and closer to this real value of the actual area. So we would write that in mathematics as we'll call it the width, W. Now, later on in maths, you'll learn other terms for this, but let's just call it W for the time being. So as W gets smaller, that is, as W gets closer and closer to 0, the sum of all the rectangles, remember we can use this to mean sum, so the sum of the rectangles gets closer and closer to the real area of the shape. And this idea that something is getting closer and closer to a real value is what we call in maths a limit, because the limit that this will get to as we get closer and closer is the actual area. And we would write it like this, that the area of that shape is the limit, and I'm just going to write LIM for limit, as W goes to 0 of the sum of the rectangles. Now that's not a properly technical way of writing it, but it's just an introduction to that concept and that way of writing it. So that there is an application of the Riemann sum, that is adding up rectangles that are narrower and narrower and narrower until we get to the actual area of an irregular shape. So where does that leave us and how does that relate to coronavirus? Well, sometime during the coronavirus media coverage, and heavens knows there's plenty of that, you'll have seen a graph that looks like this. The red area being what would happen if we don't do anything to prevent the spread of the virus, and the blue if we do, so no intervention versus intervention. And we've all heard about flattening the curve. So let's have a look at how what we just did relates to that. Let's say time since first case. Now it doesn't tell us on this graph, but let's say this was, I don't know, 10 days in at that point there. And let's put a vertical line in to show where that would be on both of those shapes. So we'll put a vertical line in there. Just there to show where we would be in both of those shapes. Just there. Okay, so that creates two new shapes. The first one is the red curve. So just pretend the blue one's not there for a sec. And you've got this shape here. Then you've also got the blue curve. So pretend the red curve's not there for a second and have a look at the blue curve. And so you've then got this bit in here. And let's compare the area of those two shapes. Now, remember, why do we care about the area of those shapes, the area underneath the curve? Because if you remember where we started, the area under the curve equals the total number of people sick. So, with no intervention, if I'm planning the public health response to this virus, I'm looking at this red curve and saying the total number of people sick, the area of that red shape, calculated by using a Riemann sum, is enormous. However, if I look at the blue shape, this little bit in here by day 10, then that's quite small. Now, why is that important? Why is it important that we keep it small at day 10 rather than having it big at day 10? Will it reduce the total number of people that get sick over the whole course of the virus? Well, maybe it will, maybe it won't. But here's the important line that's missing from that graph. So let's bring our ruler back in, and let's put in a horizontal line this time. And this line here, which we'll put in blue, shows how many people our hospitals can cope with at once, right? So we'll run that across there like that. And that's the important line. If I've got this number of people sick, and that's my hospital's ability to cope, then all those people above that line, all the people in here who are sick, cannot get hospital treatment. However, this is well below my hospital's capacity. In fact, that curve never gets to the hospital's capacity, which means everybody can get treatment. So this concept of the area of an irregular shape, the area under a curve calculated using our Riemann sums, is critical for planning and understanding how viruses spread and how much effort we need to put in to slowing down the spread of that virus.